improvement of the stability performance of a quadcopter helicopter by Neuro controller. So please, you have 15 minutes.
Good afternoon, everybody. I will present myself. I'm PhD student Balaji Jalal in the University of Mbawaqi. Yes, I'm here today to present our work entitled Improvement of Stability Performance of Quadcopter Helicopter by Neuro Controller. So, there is currently a growth in the use of technology everyday life in drone are on of the best human invention at now. However, despite of development in field of technology, drone are still suffer from a lack of stability in difficult condition. At the same time, the quadcopter helicopter has attention because of its very good flexibility, its ability to perform variation of our area mission even difficult condition. That quadcopter helicopter can adapt variety of fly attitude, which attributed to the efficient against speed controller with about form probabilities and on order to enable the quadcopter helicopter to better completed fly mission. Fly stability performance become particularly important. A neurophasic controller algorithm AMPHIS proposed in our work to answer the stability performance of a quadcopter. So, what is it? The quadcopter? A quadcopter format is of four propellers, each rotated with the aid of motors and a pair of guides which serve the decrease of speed, rotation of and stability to answer the torque product. The propellers 1 and 3 rotated counterclockwise, while the propellers 2 and 4 rotated clockwise. So, how we can define mathematically the quadcopter? The following axis convention is chosen. Here we can define the movement of our quadcopter. They have 6 degrees of freedom. Translated with the x-axis and the y-axis and z-axis, and the rotation about the axis 3 axes, x and z and y. For definition our mathematical model of our quadcopter, we can at the beginning the movement of reference mark it's close in the with fixed reference mark. After the moving reference mark makes a rotational movement about the x-axis by roller angle. The phi it's limited by negative half of p and the half of p angle, and followed by rotation about the z-axis of angle. Phi it's limited by negative p and p, and we have here matrix called R who defines the oral angles. And this is picture explain the talking about oral angles. Secondly, we have angle of speed, rotation speed, omega 1 and omega 2 and omega 3, and fixed reference frame are expected as the function of the rotation speed, phi and theta and phi in the movement of a reference frame. We have the omega matrix, and this is picture described our matrix. When quadcopter makes small rotation, the following experimentation can be made, and this is question, and this is function. So the angle velocity will be this is vector. And third one, we have linear speed. Linear speed VBX and VBY and VBZ in fixed reference marked as a function of linear speed. Vmx, Vmy, Vmz in the movement reference form are given by V. And this picture can define what we've seen about the linear speed. Fourth one, what is the AMPHIS controller? The AMPHIS system applied in this is learning machine of neural network to fuzzy inference technique. Another term AMPHIS is fuzzy inference system SIF. Was a parameter to membership function adjusted using the propagation learning algorithm to the combination with another type of algorithm such as the last square, and use the genetic algorithm to show AMPHIS learning parameter. The number of iteration it's 20, and the number of membership function it's 5, and finally we have 0.4 zeros of error tolerance. The AMPHIS architecture proposed in this next figure is multi-layer network whose the connections are not white or all white of one. The need or of two different type according to their functionally. The square node adaptive connected parameter and need circular fixed and have tone parameter. However, each node square or circular apply the function to its input single. And this is picture defined what we see about the AMPHIS controller. Applied AMPHIS controller on quadcopter. In this part, we generated the trajectory based in rotation of function in order to have trajectory without decoupling form in initial point with a zero speed and reach when a determined final point the same zero speed. Next, complexity, the present or the expression of the position variable that generated a cone as we will as figure illustrating in chart. We have here expression of trajectory in X and Y and Z. We can see the following figure is the trajectory of the XF drawn following desert or trajectory, the reference. We have here in this picture, we can see the reference of our drone. The robustly study. From figure 1 and figure 2, we notice the error of the AMPHIS controller much smaller than of the fuzzy PD controller, but nevertheless, the controller by AMPHIS controller present oscillation with increase increase of degree force with which can distribute a drone. Here we have a picture who define stability of our drone with AMPHIS and the stability of drone with PD fuzzy. Here is picture we have 4 force. We want to apply the contrast of the 2 force, and here the 4 force. In this figure showing our controller system ensure the continuation of the complexity in the path. Part will be showing our controller system ensure the connection, the complexity trajectory, and we notice that the error tended towards 0, so deserted position and the research. Like conclusion, it's part from this work that the use of the architecture called AMPHIS is simple and efficacious, while the obtained by interpret in the form of decision rules. We have found that the used a simplified structure or allows it use to obtain an efficient command law by only learning with intervention of the genetic algorithm to show the learning parameter of the amphis. The controller result used amphis showing the validity of the approach for ordering our system. So, the technique have been successfully applied to design controller algorithm that moving it drawn from initial position to desert equilibrium position of simulation result confirmed the controller performance used. So thank you for your attention.
Thank you very much. And also it's time for questions. Yes, please.
Yes.
Can we make a program to program this drone for missions? To give them a mission, to make a mission with a program, not just command control.
Yeah, thank you. When we need to make some drone to go into mission, we need to make it auto controller to give him trajectory or destination. The drone can go to the destination and give what we want to do, and they come back. That's what you need. En français. Le moment qu'on a besoin de programmer une drone pour faire une mission, il faut que nous mettre autoprogrammer, autocontrôle. Il suffit que nous lui donnions une tâche et elle va automatiquement pour le réaliser et revient tout simplement. Dans une autre de les cartes graphiques qui existent dans notre marché en Algérie, le monde entier actuellement, il n'est pas possible de faire une drone de simple small drone, zero drone صغير ونقدروا نبعثوه يجي لنا يدير لنا ميسيون ويرجع. ما خطركش لي كارت جراف الميكرو كنترولور اللي اكزيستيو دركا كاش ميكرو كنترولور قوي يروح يدير لنا دي ميسيون كيما هادو ويرجع. يكون المشكل تاعنا في الميكرو كنترولور. المشكل دركا في الميكرو كنترولور، المشكل ماهوش في الدرون بعد في حد ذاته يقدر يدير دي ميسيون اريان كيما المشكل في الميكرو كنترولور.
Other question? Please, please.
Point of view, in electrical networks, we use drones
Yeah.
for example, we have a tree or a plastic that falls in the area line,
Yeah.
in the cables. So we send the drones to turn off the fire. So it relates the circuit current.
Yeah.
in this business. That's why I asked you this.
Yes, we can. If not send him away, you can do it. That. I'm need to you ask it to go into the kilometers. We cannot send the drones to do mission in kilometers. We must make it close for us to send him the controller and come to control them. Yeah.
Other questions in the room? Other questions or remarks? Okay, few questions, very quick questions. Actually, for this, you propose to control the drone, and you put some restrictions on the angles, for instance, between minus pi over 2 and minus 90 degrees and 90 degrees. What's happened if I want to do this? Actually, you can do until this, you cannot have 90 degrees, plus or minus. If I want to do a mission where I need to move, for instance, like that, what's happened in this case? And what would be the solution in terms of modeling or control or build to resolve this problem? And you know the problem is coming from singularity in the model.
Yes.
So if it's singularity, how to avoid singularities? Have you any ideas on that?
I will answer your first question. Yeah, the first question you asked me what will happen if we will make our drone in the perpendicular.
Yes.
Yeah.
Fall down. Okay.
Fine.
Okay. Nice. It falls down because of the controller, because of the singularity that will generate something which is
It's
false.
always-
What's happening exactly?
It's always about the frequency of our controller. Yeah.
Frequency?
The frequency of our controller.
What do you mean the frequency?
Of the test controller.
The frequency, the sample time?
Yeah, you can see that. But when we make it the capital PG in drone, when they calculated the angular and corrected that, but when we make it the sample control sample processor in the drone, they will not.
No, no. There is no link between frequency and this problem. This problem is singularity. And singularity which generates a mathematical problem, like 1/0, which goes to the infinities.
Yeah.
So this is
There we
how
go.
so how we can avoid this problem. Have you any idea?
No, I don't know.
Actually, in your model, you use which angles to model your system?
Oh, good.
You have introduced the angles. Which angles you are using?
Angle about the round of the X and
Yes. How we call these three angles? How we call them? The Euler
Euler and
angles.
Euler.
And to avoid this problem and to go through singularities, did you know the method of quaternions?
Not
The quaternions, you can have a look. So it's a method that enables you to go through singularities, even with the angle 90 degrees, 99
This
degrees.
is problem I will try to them and see them in YouTube in this problem, but I'm not.
Okay, no problem. Then also when you have presented the sense of rotation of the propellers of the quadrotor, yes, please. So if you want to move in a certain direction, sometimes you need to change the sense of rotation. At the beginning, I think it's at the beginning when you show the diagram, more. Yeah, here, yes.
Yeah.
Here, it depends on what you want to do. You have to choose the sense of rotation of each propeller.
Yeah.
I mean, if you want to go this direction, or
Yes.
or rotate, or so there is. So how you switch? For instance, I'm going like that, then I will go down. How you can switch between the different sense of rotations while controlling the.
When I want to go with to the X, I will
Slow down.
slow down the controller of the because of the rotation speed up our motor, and they will go in further. And slow up of the rotation.
Speed up.
Speed up of the motor, like the 3 on 4, and they will go
And maybe you need to do this very quickly, because if you stop, you reduce the speed. Maybe the.
Yes, I do.
So you have to very quickly. Okay, nice. And another question is concerning the controller itself. So this controller and it should be trained offline, online. How it works?
Yeah, offline.
Offline.
Yes, trajectory. This is trajectory. We will make it like a data, and you can see here.
Yeah.
Trajectory about the
This.
X and Y and Z. We can make it see the data and run it and this in MATLAB, and you can run it offline.
Okay, nice. And the slide where you saw the results, the curves of the tracking.
Which one?
Here it's what you have to curves. Go down more. No.
I go down?
Down.
Yeah.
Stop. No.
Yeah.
Go back. No. Here.
Yeah.
Here, just a general remark, because actually we.
It's trajectory of about X and Y.
Yes, it's good. No, I just want to make a remark, because we have all the time this kind of presentation of results in robotics, whatever the robot is.
Yes.
It can be manipulator or drone or underwater. We want to show the tracking of a reference trajectory. So actually, if you obtain a result like that and you show it as it is, we cannot see anything, because actually the trajectories are very, very close. So the tracking error is very small. So here, maybe we can see just the kind of the trajectory itself. So we go from here to here.
Yeah.
So if you want to show the degree of tracking, the precision of the tracking, you can keep this, but other curves where you show the tracking errors. The tracking error, even if it's small, 0.1, you will show it how it evolves. You understand? It's just more remark than a question. Did you try to, yes, the test of the robustness, I didn't understand exactly what did you modify to test the robustness. You show some results, I think it's could you please just explain maybe better? Yes, here for instance. Robustness. What did you modify exactly to test the robustness?
The forces were applied on the draw.
Yeah.
Yeah. We have here applied the same draw. We have applied in the PED, fuzzy PD, and we are compared between the result of the fuzzy PD and the Apis result. We have here in this picture, we applied two forces in our draw.
Yes, I want just exactly, this is my question.
Yeah.
I want to understand better which kind of forces, external forces applied to the drone. It's the wind force, I guess, maybe. So they say wind. And how? What is the exactly this force? It's constant. It's time varying.
We can apply the forces of in the axis.
The z-axis. And the force is constant, time varying. What's it? Constant.
Because it's just
just impulse. Okay, nice. Just the one impulse. Yes. Because actually the problem of drones is the wind, for instance. Yes. And sometimes it's
I hope to work in the deep learning and attack them by some force.
yes. Okay. So thank you very much. Let's thank again the speaker.